Welcome to Extra Continuity Problems. Today we're just going to talk about some standard stuff that you might see. And so first I wanted to give an overview of what we're thinking when we're thinking about continuity. So we talked about our continuity checklist. If you're ever seeing if something's continuous at a point, you check essentially three things. First, you want to make sure that the point's actually defined. If it's not defined, it's automatically discontinuous. If it is defined, it's not guaranteed to be continuous. It just means you can move on and check the next thing. So it is possible for f of a to be defined, but the function to not be. Next, we need to know that the limit as x goes to a actually exists, that's defined as well. So those are two different things we want to check, and both of those have to be true in order for us to have continuity. But just because they are true, that doesn't necessarily guarantee us that the function is continuous. Once we have this third thing, that these two numbers that we get are the same, then the function's continuous. So you get the limit, that exists, you can plug in, that works fine, and the two numbers that you get are equal to each other in the end. Once all three of these things are true, the function's continuous. If even one of them is false, your function is not continuous. And so there's three types of continuities, or discontinuities, at least in this class that we'll see. And so one of those is the removable discontinuity. And that looks something like a function that does this, and then it just has a little hole in it, and then it just keeps going. Or possibly, so call this f of x. Or possibly we have a different function like g of x down here, where g of a certain point is defined. So here it's a, g of a is defined. The limit exists, but they're not the same. And so these are a removable discontinuity. You have a removable discontinuity when the limit does exist, but the function is not continuous. So that's how you know it's removable. If you try to figure out the limit and you do get a number, but either the function doesn't exist at that point or it does exist and it's completely different. Next is the jump discontinuity. And so that would be something that looks like this, where you have a left limit and you have a right limit, but the two are not the same. So in particular, the limit wouldn't exist then because the left and right limits are different. And so that's how you tell algebraically that you have a jump, is you can find the left limit, you can find the right, but the two numbers that you get are different. That's a jump discontinuity. And the final kind is a function that goes off to infinity. It only has to happen in one direction. And if you have this, then that is an infinite discontinuity. And so you can tell that because you try to plug in and you get like some number over 0. And that means you have an infinite discontinuity. So those are the three types. And we'll see examples of all of these two. How do you see this like algebraically if you're working with problems? All right, so first problem is determine if this function f of x is continuous at a certain point. And it also says if it's not continuous, then determine the type of discontinuity. So not just decide if it's continuous or not, but actually figure out what kind of discontinuity does it have. So here we're going to use our continuity checklist. Continuity checklist we'll go through, and we'll try to see what's going on. So first, can I plug in -2? Let's see what happens. So I get -2 squared. Let's be very careful and put that in parentheses. Plus 6 times -2 plus 8 over -2 squared minus 5 times -2 minus 14. And so if we do that, we get minus 2 squared is 4. Minus 12 is negative 8, plus 8 is 0. Here we have a minus 4, or minus 2 squared is 4. Minus 5 times minus 2 is plus 10. Let's just write it out so I'm not confused. 4 plus 10 minus 14. Biggest tip I can give is don't try to do too many steps in your head, because I was about to mess myself up there. So 4 plus 10 minus 14, yep, that's 0. So we have 0 over 0 form. And for limits, that means we have more to do. But for the function itself, that means it's undefined. We're trying to divide by 0, and we're not allowed to do that. Okay, so f of minus 2 is undefined. And so since f of minus 2 is undefined, that automatically means f of x is discontinuous at 2. So at x equals negative 2, in fact. And so now we have to figure out what type of discontinuity it has. When you're trying to figure that out, you want to take a limit and see what happens. So here we look and we see the limit. All right, there's no like weird stuff going on. This is just a kind of standard thing. We have a 0 over 0 form, so that's a removable discontinuity. And so then the limit as x goes to minus 2 of f of x is the limit as x goes to minus 2. And then we look, and this looks like something we could potentially factor, and the 0 over 0 is another hint of that. So let's try factoring out. So x squared plus 6x plus 8. I need two numbers that multiply to be 8, add to be 6. So that's plus 4 and x plus 2. On the bottom, fraction bar is giving me some issues. On the bottom, if we look, we need two numbers that multiply to be minus 14. So they have different signs as each other. And they need to add to be 5. Now if we look, if we think that's a minus 7 and a plus 2. So x minus 7 and x plus 2. But now because I'm taking the limit, perfectly fine to cancel the x plus 2's. And so I'm left with the limit as x goes to minus 2 of x plus 4 over x minus 7. That's negative 2 plus 4 over negative 2 minus 7 is 2 over negative 9. And the really important thing is that it exists. So here, limit as x goes to minus 2 of f of x exists. If you're discontinuous at a number, but your limit exists there, the only possible way that can happen is f of x has a removable discontinuity at negative 2. So just write that down messily. Continuity at x equals negative 2. And why is it removable again? One more time, just to really hammer it home. Why is it a removable discontinuity? Because the limit exists and it's not continuous. So that's how we know. That's the tell that it's a removable discontinuity. New problem, new function, but it's still asking us, is this continuous at x equals 7? And then it says, again, if it's discontinuous, determine the type. It's good practice to be able to determine the type because you might get to problems where it doesn't ask you to do that. Well, then that's just a little bit easier. So here we want to see if this is continuous, in which case we go through our continuity checklist. First, we see if we can plug in this number, 7. So we try, we get f of 7. If I try to plug that in, I get 7 squared minus 4 times 7 minus 5 divided by 7 squared minus 8 times 7 plus 7. On top, that's 49 minus 28 is 21. minus 5 is 16. On the bottom, I get 7 squared is 49, minus 8 times 7 is minus 56, so that's a minus 7 in total. Plus 7 is 0. So I have 16 over 0, which means I can say two things because of that. First, f of 7 is undefined, which also means f of x is not continuous at the point x equals 7. It also tells us a little bit more, though, that when we start looking at the limit, that it's infinite. So we know the limit as x goes to 7 of f of x is either plus or minus infinity. We don't know which one, but we know it goes to one of the two, and so then we can automatically conclude it's an infinite limit. And the reason we know it goes to infinity is we have a number over 0 where the top number is not 0. So anytime this isn't 0 and you're trying to divide it by 0 when you take a limit, automatically means there's some sort of infinite limit thing going on. Here I need to be a little bit careful, though. I need to say from the plus or the minus. It could be that this function goes to two different infinities, but we do know it goes off to one infinity or the other. Some good extra practice, just in case you're asked to graph something, or in case you're asked to do infinite limits, is figure out what does the left limit go to, plus or minus infinity? What does the right limit go to, plus or minus infinity? Could be some good extra practice. But because the limit is infinite, we say f of x has an infinite discontinuity. Brand new function, h of x. Now it's a piecewise defined function. So hopefully you're already kind of suspicious of what's going to be happening here. But let's read it. So h of x is this piecewise 2x plus 4 if x is less than or equal to minus 5, minus 3x minus 7 if x is greater than minus 5. So determine if this guy is continuous at x equals minus 5. If not, determine the type. First thing we try is, can we even plug in? So if I try to plug in h of minus 5, well, here's where it's less than or equal to minus 5 on that top row. So that's just 2 times minus 5 plus 4, which would be minus 6, because it's minus 10 plus 4. So we do get a function value. And so again, there's some confusion. That does not make the function continuous here. It just means we can plug in. It means we haven't disqualified it yet. So now we'll try 2. We try to plug in the limit, see what happens there. And now, since this is a piecewise defined function with less than or equal to and greater than or equal to at 5, that means we have to check the left limit and the right limit and see if those are the same number. So the limit as x goes to minus 5, first we try from the minus side. Well, from the minus side, as I think about it, like I'm plugging in something a tad bit smaller, so something like 5.001 is how I'm imagining it. That corresponds with this top row. And so we get a repeat of what we already wrote. H of x is 2 times minus 5 plus 4 is minus 6. Next, we check the right limit. We make sure that that works. Minus 5 from the plus. And now from the plus side, we have this minus 3x minus 7. And if I'm picturing this in my head, this is something like minus 4.999. I'm a little bit bigger than minus 5. So I plug into this, I get minus 3 times minus 5 minus 7. That's 15 minus 7 is equal to 8. And now these two are not equal. And what that tells us is that the limit doesn't exist. The limit as x goes to minus 5 of h of x does not exist. And so now we have enough information to determine what kind of discontinuity is this, because the left limit exists and the right limit exists, but the limit itself does not exist because they're different. And so that's enough to tell us h of x has a jump discontinuity. When you have a left and right limit and they're not equal, that is a jump discontinuity. Continuity. Okay. And just as like a quick aside, this is the answer to the problem. But I do want to say, if number 2, if we check these two and they were equal, they were the same thing, then the limit would exist. And then we would check, is that the same as the function value? And it would have been. So don't immediately assume because it's piecewise that it has to be a jump discontinuity. But be very, very suspicious because most of the time that intuition will be right. Now let's shift gears a little bit. Instead of saying is the function continuous or not or why, now let's make some functions continuous. So here the idea is the intuition I want to give you is essentially you want to make the two functions equal. There might be some caveats to that, like we'll see. But definitely when you have less than or greater than or equal to, the idea is you want to set them equal to each other at the point that they share like this. So for example, here it's going to be x equals 1. What's the nice way to show it? What's the very precise way that no mathematician could ever argue with? So we want to say f of 1 is always going to exist. That's not going to be a problem because x greater than or equal to 1 and we have a polynomial. So the issue is we need the limit as x goes to 1 of f of x to exist. And we're very specifically talking about 1 because that's the only thing that could possibly be a problem spot. Everywhere else, I'm always using one of the functions when I get close. And so there's no worry about the limits. But very specifically at 1, I could have a problem. But that's really easily handled. I just check the left limit. 3 times I can plug in 1 plus 1. That gives me 4. And then the right limit is 5 times 1 minus k equals 5 minus k. And now we want to set these two equal. So 5 minus k equals 4. Do some algebra, plus k to both sides. 5 is equal to 4 plus k. And now move the 4 over and get k is equal to 1. And so the idea then is if we plug k equals 1 in and we look at the graph, these are two lines with different slopes, but they connect together at x equals 1. So it's a perfect something like here's 3x plus 1, and then it immediately boosts up to 5x minus k. But they touch right here, like a little elbow joint. One more time, find the value of k such that g of x is equal to this honkin' function. And the thing that I want to point out, the thing that's different here is instead of like greater than or less than on both sides, which is the normal thing we see the majority of the time, here we have not equal to and equal to. So in other words, it's this top function the vast majority of the time, and then at one very, very, very specific point, it's this number k here. Everywhere else, though, it's the fraction. So find the value that makes this continuous everywhere. So we already know g of 6 is going to be k, so there's no issue plugging in. We just have to find the value. Right, so g of 6 is equal to k. And the reason we really care about that here is because The not equal to makes us need to find the limit, makes us need to find the function value, and set those equal to. So it's the same general idea, but it's just a slight bit different, a little bit mixed up compared to what we were doing. So the limit as x goes to 6 of x squared minus 4x minus 12 over x minus 6. If I try plugging that in, I get 36 minus 4 times 6 minus 12 divided by 6 minus 6 gives me a 0 over 0 form. Well, that's indeterminate. So I have to find something new to do if I just plug in. And so my solution to that is factoring. X minus 6, x plus 2. I needed two numbers that multiply to be minus 12, so they have different signs, and add to be minus 4. On the bottom, I have just regular old x minus 6 with nothing else. I can cancel those then, and I have the limit as x goes to 6 of x plus 2. Then I can just plug in and get 8. So I have 8 here, and I want to be a little bit careful. I'm not quite done yet. But what I need to do is I need to set the function value equal to the limit value. And so now I can say k is equal to this limit value, which was 8. And that is my final answer.